Another beautiful day in pre-calculus land. Today what we're going to do is we are going to take a look at one of the appendices in the back of the book here. There are a lot of skills, prerequisite skills that we need in this course, and we need to make sure that everybody remembers what they've learned in those past years as we move forward. So Pre-Calc Appendix A1, here are the objectives. We want to simplify and evaluate radicals and rational exponents. And the radicals here, notice it doesn't say square roots. Last year in Algebra 2, we learned how to deal with an nth root, any index that we have. And rational exponents, not a big deal. We learned that last year too, that you can take any radical and you can change that into a fraction. Remember, root word for rational is ratio. And often that'll make the math a lot easier. We're going to reduce, factor, and simplify rational expressions. We're going to rationalize the denominator. Remember our rule that you are not supposed to leave a radical in the denominator. And that rule is going to hold quite a bit of the time for what we do in here, but there will be times when the book flat out says, don't bother rationalizing the denominator because the math gets kind of hinky. So we will rationalize the denominator and we will rationalize exponents. So these are the things we need to do. And down below here it says this section is specifically to help us practice manipulating expressions using skills and properties that we've learned in the past. And most of it's going to come from Algebra 2. We might be a little bit rusty. Skills will definitely improve by implementing a simple three-step procedure. Obviously, you need to practice and practice and practice. And that's because I teach it to you, it's in your short-term memory, but by golly, if we start to practice that, our brain says, hey, this is important and I need to remember how to do this all the time. So that's where we want to go. A1, radicals and rational exponents. And our objective is simply, let's review those properties of radicals and rational exponents to begin with. So the definition, the real nth root of a real number. And hopefully when you read that, that brought you back to this, where we're taking the nth root of some real number. It says let n be an integer greater than 1, and a and b are real numbers. If we can take a real number b and raise it to the nth power and get a. Remember, whatever we do in mathematics, we have to be able to do it forwards and backwards. So there has to be a point when, and let me rewrite what they have here, when we could say, well, we're going to take the nth root of b to get b by itself. But we know in algebra, whatever you do to one side, you have to do to the other. So if this is true, then b has to be an nth root of a. And that would be, doing this process, we would see the nth root of something to the nth power just gives you b right back. So it's simply solving, but using variables instead of numbers. Like we used numbers a lot in Algebra 2, but we also did experience some variable manipulation. If a has an nth root, the principal nth root of a is the nth root having the same sign as a. So in this situation where we have an nth root of a, when we have an even index, and n is the index there, we would normally say that there is a positive and negative answer to this, a plus and minus answer. But this is saying for the principal nth root, just look at what you have underneath the radical. That's called the radicand. And whatever sign that has, the principal nth root gets that same sign. So the principal nth root is denoted by the radical expression, the nth root of a. And the positive integer n is the index of the radical, and a is the radicand. So every part that we have when we write the nth root of a has a name. And the names are this little n, the number that goes inside the v, that's called the index. The entire thing altogether is called a radical. but this A, specifically the number that we're trying to evaluate, that is called a radicand. A radicand. So we have vocabulary that way. If we're taking the cubed root of 3 and somebody says, well, Cedarholm, I have a problem with that 3. Well, my question would be, which 3? What are you talking about? You talking about the index? You talking about the radicand? And that way we could speak to the issues that people are having. When n is odd, so when the index is odd, every real number has exactly one real nth root. And that's because that index has to work backwards from powers. So if that index is odd, let's say that we have a cubed root of some number, we're saying that there has to be some number that if I put it in these parentheses, that exact same number each time has to give me the radicand. And so if they're having us evaluate a number that's negative, well, for cubed root, your answer will have to be negative. If they have us evaluate for a radicand that's positive, then we'll have to get a positive answer. So there's only one real nth root. Now when n, the index, is even, now that's different. We know that. For instance, in Algebra 2, when you had to take the square root of 16, you knew that you could get two answers. It could be a positive 4, it could be a negative 4. So when n is even, positive real numbers have two real nth roots. Notice that 16 is positive, so we have two real nth roots. However, negative real numbers have blank real nth roots. So now they're asking us about this situation. And they're saying, what's going to happen? Well, if we remember our math from last year, we know that this should be a positive and a negative for I. And that's a problem because we need to know how many real nth roots it has. It doesn't have any. It does not have any. So when we're taking an even root of, as it says there, negative real numbers, we're not going to have any real nth roots as long as that index is even. Now, we've got the square root of a, and it says we should all know that there's a little bitty 2 in there for the square root of a. So when we think of the square root of 16, we should think, what number or numbers could I put in those two positions so that the number is exactly the same both times that would give me 16? And that would be a positive 4 and a positive 4, or a negative 4 and a negative 4. You can think of this process as working forwards and backwards from raising things to a power. So the square root of a is the square root of a where the index is 2. But we don't write the 2 down. It's just assumed to be a 2. Just like if I write x, you assume that it's 1x. If there isn't a number out in front, it's a 1. In this situation, if there isn't a value for the index, it's because it is a 2. If a is a positive real number and n is a positive even integer, its two nth roots are denoted by the nth root of a and the negative nth root of a. So for our 16, they're saying if we go ahead and take that square root of 16, we'll get a 4 and a negative 4. So those are our two solutions. So down here in example 1, we see there is a little piece of information off here to the side, and that is that most calculators do have a key for the principal nth root, and we can use that feature of our calculator to check the computations in example 1. And just so you know, that's always underneath the math key. So if, for instance, and the calculator is going to yell at us on this one, we want to punch in the fourth root of negative 625, we would punch in a 4 math, and then we'd find our generic root key. You're going to notice underneath math that there is also a cube root key, but that's not the one we want here because we want to be able to pick it. So we're going to need to go down to number 5, and then we would punch in our negative 625 on the main screen. And when we do that, we're going to get a message that yells at us. Now, why did it yell at us? Why does the calculator yell at us? Because the fourth root of negative 625 is saying that there is a number that I can write inside each and every one of these parentheses that will somehow multiply to a negative 625. And we know that's impossible. And that's because either all four of these would be positive, which would give us a positive answer, or all four of these would be negative, which would give us a positive answer. There's no way to get a negative in the real number system. So this one doesn't have any roots. So finding principal nth roots, we have the square root of 36. We do need to notice that this said principal nth roots. I know for A we'd really like to write down positive and negative 6. However, notice that principal root has to have the same sign as the radicand. And that 36 this time is a positive 36, so we're only going to give an answer of 6. For B, we have the cubed root of the fraction 27/8, which looks a little overwhelming at first until you remember that you can split those apart. And you can just think of that as the cubed root of 27 and the cubed root of 8. So now think about those three slots and think what number would need to go into those three slots to give you 27, and that would be a 3. And what number would go in those three slots to give you 8? And that number would be a 2. And then stop and think, well, is it a positive? Is it a negative? Is it both? Well, this is cube root. And with cube root, the only way this is going to give us a positive 27/8 is if a positive 3/2 goes into each one of those parentheses. Now, you can see the difference in C. The 27, that's not different. The 8, that's not different. But now this one is going to be negative. And we realize we really could use the exact same thinking that we used right here and know that that's going to be a negative 3/2 to make that happen. If you wanted to think about this from the start, just like you did for B, you could think of this as the cubed root of negative 27 over the cubed root of 8. Or you could think of it as the cubed root of 27 over the cubed root of negative 8. But notice you only take one of those terms as a negative. The negative goes with the numerator or it goes with the denominator. You never put it in both because that would mean it's positive, and it's not. It is negative in this situation. All right, let's head on down to E. This is the fifth root of 32, which again means 1, 2, 3, 4, 5 slots. And we want the same number in every single one of those slots. That would give us 32. And again, we need to think, all right, this is fifth root. Well, if it's fifth root, 1, 2, 3, 4, 5 slots, it can't be a very big number. It has to multiply to 32. So you think about it and you realize that's going to be 2. 2 times 2 times 2 times 2 times 2. And this is an odd root, so positive 2 is the only thing it could possibly be. Because if we put negative 2's in all 5 of these slots, we would come back with a negative 32. And that's not what our radicand is. It's a positive 32. For F, we want the fourth root of 625. So 1, 2, 3, 4 slots. We want to fill them with exactly the same number. Hopefully from last year you remember that 5 to the third is 125, and that kind of piques your curiosity. And you could certainly use your power chart for now to verify that it's going to be 5. So we look at this and we're thinking, all right, we are really saying this. And we want to talk about a principal root. Well, what we have under the radicand is positive, so we are not going to say positive 5 and negative 5 for this fourth root. We're just going to say 5, and that's because the instruction said principal root. That's what we're looking for. G, well, we already did this. The cubed root of negative 27, that was part of this, and we used this problem to get there. So you think about those 3 slots, and you realize it's definitely going to be a 3, but it's cube root and it's negative 27. so it needs to be a -3. So you can kind of split it up into two pieces of figuring out what number it's going to be that you need, and then talking about, okay, does it need to be positive, does it need to be negative? H, this is a sixth root. So in my mind, I'm saying 1, 2, 3, 4, 5, 6. Oops, I'm going to run out of space. There's so many of them here. Let me try and give myself a little more work room here. And I know it has to be a very small number. So I start thinking, well, wait a second, we just had the fifth root of 32 over here. So if I put one more 2 in there, 32 times 2 is going to give me 64. So again, this is an even root. We're tempted to put plus and minus 2 here, but principal root says match the positive or negative value of that 64, and it's a positive 64. So our answer would be a positive 2. So principal roots, we have to think, what is the value for the radicand right now? Is it positive? Is it negative? And that will determine what we write down for that principal nth root. Properties of radicals. Looks like there's a lot of them, but this is all review. So properties of radicals: let u and v be real numbers, variables, or algebraic expressions, and m and n be positive integers greater than 1. We assume that all of the roots are real numbers and all of the denominators are not 0. So the first property that we see here is a pretty basic one, and what that says is if you can tear these apart to simplify them, then you should do that. For instance, the square root of 50, we would break that apart and pull out a perfect square factor. The square root of 25 is the perfect square, the largest perfect square that divides into 50. And that would give us 5 square roots of 2. That's something we've done for years. You know, you did that in exponential, you did that in algebra 2. In fact, you did some of that in geometry in the second semester working with some of those radicals. So here you see the square root of 75. And again, we think biggest perfect square that would divide into that evenly, well, that would be 25, and it goes in 3 times. We separate those two so that we can write that as 5 square roots of 3. And it doesn't matter if we're talking about the product, multiplying those together, or if we're talking about division. We can separate them if that's going to make the problem easier. So we separate these two and think, all right, 4th root of 96 over the 4th root of 6. How is that going to help me? Well, those are already separated, so maybe they're trying to hide something from me. Maybe I better put those back together and see what's going on. So 96 divided by 6, well, that'll give me 16. And the 4th root of 16, the principal 4th root of 16, is going to be 2. We get to number 3, and this looks a little bit scary. It's not as scary as it seems. It says if you take the mth root of the nth root of u, it will be the index of m times n square roots of u. Well, let me talk you through the example they have. They have the square root of the cubed root of 7. Here's how you think your way through it. This is obnoxious. I mean, this radical inside a radical thing, yuck. So what I'm going to do is change this to fraction powers, and I realize this is a little 2. So inside here I have 7 to the 1/3 because that's how fraction powers work. Your index is always your denominator. Remember that index is the root piece, and your root always goes into the ground. It is the denominator. So we have 7 to the 1/3, but then that has to be raised to the 1/2 power. Okay. But when you have a power to a power, you're supposed to multiply those two powers together. These are fractions, so we do top times top and bottom times bottom. That's going to be 7 to the 1/6. But when a problem comes to us with radicals, we are to give an answer in radical form. So we should say, wait a minute, 1/6 power, that's the same thing as the 6th root. And it is. So just using what we know about fraction powers, and yes, I know this looks horrible right here, but it is something that we already know how to do. Number 4, this just makes perfect sense when you look at it. You see you've got the nth root and an nth power there, and if those two, the power and the index match, well then you get right back to the beginning again, which is the radicand, which is the u value. Again, notice it's a principal root here. They're not talking about positive and negative. They're just keeping this positive. So when we look at the fourth root of 5 raised to the fourth power, the index of 4 means fourth root, and then the power of 4, that's how you use inverses. Those two undo each other. It gets you right back to a positive 5 because your radicand was positive. Number 5 says, hey, split this apart if you have to. If you've got the nth root of u to the m, but this is a nice number for this index, figure out what that is first and then raise it to that power. So as we look at the cubed root of 27 squared, we do not want to square 27 right away. And that's because the cubed root of 27 is really nice. It's a 3. So we would take the cubed root of 27 and make it a 3 and then square it and get 9. So that problem is something we could do without grabbing a calculator. We want to look for those little pieces that kind of grab us as, wait a minute, if I did it this way, things would go much faster and easier. And number 6 is basically just showing us the definition of what we need to do when we're talking about taking radicals, taking roots. So the nth root of u to the n. If the index is even, we're going to look at that positive value. We're going to say that it's whatever u is and it's positive. Now here's why. If we follow the order of operations, parentheses, radicals, those are grouping symbols. So in this situation, the first step would be right here. That is step number 1, right there. You would have to raise u to that power first. Then take the nth root. And if you do that, you will end up with a positive u value. And if our index is odd, well, we all know we can get a positive or negative answer that way. So it says if n is odd, we're going to stick with a positive u value. So this is all about that principal root piece that we've been talking about. So if u, right here, we're taking the nth root of u to the n, and n is odd, we're getting one answer. We're getting u. So what are they talking about? Well, if we take the square root of -6 squared, order of operations says do this first. So -6 times -6 would give you 36. And if you take the square root of 36, we get 6. And that's because we're using that principal root concept as we go through here. So the square root of -6 squared following the order of operations would give us a positive 6. And below it you see the cubed root of something cubed. If the index and the power match, well then they just cancel each other out and we get a -6. So you have to think about your index and your power and how those two pieces work together. So simplifying radical expressions, you must know how to simplify radicals involving algebraic expressions and for numerical computations when you need exact answers. Remove factors from under the radical according to the rules. So we've got our objective as simplify and evaluate radicals and rational exponents. Reduce, factor, and simplify rational expressions. So those pieces are what we're going to work on right now. Removing factors from radicands. Well, we have the fourth root of 80. So here's what I'm thinking right now. I'm thinking, do I have any perfect fourth roots, perfect fourth powers on my power chart that will divide nicely into 80? So I go down that chart and I try to see, and I see right away 2 to the fourth is 16. Wait a minute. 16 goes into 80 5 times. So I know what the fourth root of 16 is. That's a 2. And there it is, talking about those principal roots. Again, this is a fourth root. Normally, if we had to do this as part of solving a problem, we would think about the positive and the negative, but we're focusing on the principal roots. For B, This is something you've done before. We have the square root of 18x to the fifth. So I start thinking, all right, well, I know square root of 9 and 2. You know, that's a lot of algebra 2 that you did there. But now I need the square root of x to the fifth. Gosh, I wonder if I can break that up a little bit so it'll look like it makes more sense. So how about I do the square root of x squared, the square root of x squared, and the square root of x? All right, so the question is, can you do that? Sure you can. Notice these are all square roots. So as long as they have the same index, we could multiply these back together. And when we multiply similar bases, we add the exponents. So what I have there is still x to the fifth. The square root of x to the fifth, it's just expanded so that I can show you exactly how this is going to work. So I know the square root of 9, that's 3. Then I've got this nasty little square root of 2 business. And I know the square root of x squared is x, and the square root of x squared is x. But the square root of x to the first, well, that's still going to be a little ugly square root of x. And then what we do is we put all the pretty stuff in front. So we have a 3, and we have an x times x, which will be x squared. And we have the square root of a 2 and the square root of x. So those will stay underneath that ugly radical symbol because they were things that did not work out nicely. All right, I take a look at C, and I think, well, wait a minute. They are perfect fourths. So I've got the fourth root of x and the fourth root, x to the fourth and the fourth root of y to the fourth. Hey, that's xy. Yes and no. I want you to think about this. If we put negative numbers in for x and y, would the answer come out negative? We always want to be thinking, did the author of this problem mean for us to use negatives in this problem? Especially when we have those even roots. That's what we have to think about. Well, what would happen with this is that no matter what number we put in for x, when we raise it to the fourth power, it's going to be positive. So we should get a positive answer. And no matter what number we put in for y, when we put it in and raise it to the fourth power, it's going to be positive. So we will have two positive numbers. We'll multiply those together following the order of operations. And then we'll take the fourth root. By golly, we better show people this is going to be positive. And there it is. We're going to put those absolute value bars there to tell people, you know what? We simplified this formula, but we don't want you to lose track of this. The person that wrote this problem knew that it was only going to work for positive numbers. And so we use those absolute value bars to show that. And that's something that happens whenever you are dealing with even indices. So a problem like this that had, if it had an x and a y in it, would have to be dealt with that way. And this was a fourth root, those even powers. Remember, even powers would normally have a positive and a negative root. But when this person wrote this problem, they knew any numbers you put in here, they're going to pop out positive. So we have to make sure that that author's intent is still there. Then for D, we have the cubed root of negative 24y to the 6. So I'm thinking to myself, okay, 24. I mean, granted it's negative 24, but I need a perfect cube that's going to go into that. So I think I'm going to take the cubed root of negative 8 out of there, because that'll be negative 2. And 8 goes into 24, a grand total of 3 times. And this time I'm not going to split apart my y to the 6th. And I'm just going to think through it. So the cubed root of negative 8 is negative 2. I have this nasty little cube root of 3 thing going. And then I remember, well, y to the 6th to the 1/3 power, because that's another way to write that cubed root. Well, 6 times 1/3, that would just be 2. And that'll be y squared. Now, this is just another way to accomplish what I did in part B. If you don't like that, if you'd rather have the cubed root of y to the 3rd and the cubed root of y to the 3rd and realize that that's y times y, which is y squared, you absolutely can do that. And then we put the pretty stuff out in front and keep the ugly radical in the back. So negative 2y squared cube roots of 3. And I'm not thinking about absolute value bars because this is an odd root. And with odd roots, we don't need to do that. On the next page, rationalizing the denominator. Oh, these can be gobs of fun. Rationalizing the denominator is the process of rewriting fractions containing radicals so that the denominator is free of radicals. Blah, blah, blah. That's a big way of saying we're not allowed to leave radicals in the denominator. I mean, that's one of the biggest bears that we have to hunt down when we are in Algebra 2, is getting rid of those nasty radicals in the denominator. So this is an algebraic formula here that they're showing us to do this. It's not as difficult as it all seems up here when we get to the problems themselves, but let me talk you through it. Here's what we're saying. We're going to find the nth root of u over v to the k. Well, the problem is the denominator. When we split it up, that doesn't work out nicely because the index and the power doesn't match. So what do? Well, we build it up by multiplying until we get that power to match the index. So we're going to multiply it by the nth root of v to the whatever power it takes for us to get the index number that we want. And they've got a little formula to do it. It absolutely works, and that would be n minus k. Now, what on earth are they talking about then? Well, let's say that we have the square root of v to the third, and that's our denominator. What we're saying is we're going to have to figure out another square root that we could multiply this v by to make it divisible by this 2, perfectly divisible by that 2. So I look at this and I think, well, I'd need one more because 3 plus 1 is 4. And then I'll have the square root of v to the fourth, which is v squared. Now notice they did this n minus k business, so they said we could go ahead and take the index and subtract what we have here. But that's assuming that we've already simplified. So there's going to be two ways that we look at these. And those two ways are both, to me, explained as make your index divide evenly into your power. That's what we have to do. So the method they're showing us up here would say that you've already simplified that denominator before you go forward. And like I said, it's great. It's a formula. It's fantastic. But let's get into this so you can see exactly how it works. We would separate these two in the hopes that something nice happens. The square root of 2 over the square root of 3. Nope. Neither one of those is a perfect square. So what we have to do is figure out, well, what should I multiply it by to get rid of that nasty square root of 3? Well, because the square root of 3 really has an index of 2, we're going to need another one of them. Because we need the power of that 3 to match the power of the index. Now my numerator is the square root of 6, but down here on the bottom I have a little square root of 3 squared. And the index of 2, this radical, is the inverse of this 2. So it'll be the square root of 6 over 3. And that one's done. So you want to be able to divide that index into that power evenly. In this case, it just took 2 of them. 2 divided by 2 gives you 1. Not so easy for b here. We have a fourth root of x in the denominator, and the numerator has already been simplified. So I start thinking, you can only multiply fourth roots by other fourth roots. It's going to have to be the fourth root of x to the something to make this work. So I put my little x there and I start thinking, what should I make my power? Well, it has to be something that's divisible by 4. Right now it's a 1. If I could just get it to be a 4, then it'll be the fourth root of x to the fourth. So I need 3 more. And whatever we do to the bottom, we have to do to the top to keep it equivalent. So now my numerator is the fourth root of x to the third, and there's nothing I can do about that. But my denominator is the fourth root of x to the fourth. Now that's important. The fourth root of x to the fourth, hey, that's x. But can it be negative? Whenever you have that even piece, you need to think, when you have an x or a y, you have a variable in there somewhere, did the author intend for this to have a negative value? Well, let's look. they wrote the fourth root of the square root of x. This fourth root does not exist unless this x is positive. So when they wrote this problem, they only wanted us to come up with positive values. We need to slap some absolute value bars on that x to make sure that that happens. Again, when you look at the problem and it has an even root, you have to think, okay, does this person really mean for them to be negative answers when this gets done? And you go back and you think your way through it. What powers did they use? What can I actually do that will give me a real number answer here? And then go back and put those absolute value bars on the ones that you need to. But again, that focus is only on even roots. Then C, if we split this in the hopes of something happening that's really nice, we're going to be disappointed. The fifth root of y to the third is not helping us a lot. But we focus our energy on that denominator and realize we can only multiply fifth roots by other fifth roots. So we're going to need the fifth root of y to the something on the top and the bottom here. And I need that y to the something to be evenly divisible by 5. Well, right now I have 3 of them. And so far, I've just got a little 1 here. But I know that's not going to do it because that would only make 4. And that's not going to give me what I need. So I start thinking, all right, well, next thing to do would be to get 5 of them. I'm going to need 2 more. And that will give me the fifth root of x squared y squared in my numerator, but the fifth root of y to the fifth in my denominator. So I leave my numerator, as nasty as it is, as the fifth root of x squared y squared, but my denominator is y. And I don't bother thinking my way through whether or not I need absolute value bars because this is an odd index. So odd index, we don't need to worry about that at all. It's just with even indices that we have to think about whether or not we need absolute value bars. D. Oh, well, that one looks pretty easy, and there's no x's or a's and b's or anything, so I don't need absolute value bars. I'm liking those. This is very similar to what we did in A. If we have the square root of 3, we're going to have to multiply by the square root of 3, so this will say the square root of 3 squared, and that will give us a 3 in our denominator. And we'll have 2 square roots of 3 over 3. Then for E, this one's a little tougher. We notice we do have a variable down there, and it's 2. You can't divide that by 3. We've got to build that up. So I start by writing the cubed root of x. And I think, what number would make this work? Well, in this case, this is a 2, and this is a 3. We need to build that 2 up to be a 3. So all we need is 1 more x. And what we do to the bottom, we do to the top. So this will give us 2 cubed roots of x over, and this will be the cubed root of x to the third. Okay, well, I can't do anything more with that. Oh, that's starting to look like a negative there. Let me clean this up a little bit. Maybe scoot it down. But the cubed root of x cubed, that's x. And then I think, well, this was an odd root, so I don't have to worry about absolute value bars. It's going to be 2 cubed roots of x over x. F looks a little nasty. Let's see how we can deal with that one. First, let's separate this. So it'll be the 7th root of 1 over the 7th root of a squared. You realize the 7th root of 1 is just 1. We don't need that radical up there anymore. But we got trouble in the denominator. 2 is not going to be nicely divisible by 7. Give us a really obnoxious fraction. So if this is a 7, I'm going to need to build up, trying to squish this in here, and it is making it really hard for you to read what I have. I'm going to have to build it up to make sure that I can take a 7th root. So you can only multiply 7th roots by other 7th roots. I'm going to need an A. And I think, all right, I have 2 of them, but I need a number, the next number, that's divisible by 7. So it's not going to be 3, it's not going to be 4, it's not going to be 5, it's not going to be 6, it's going to be 7. So I need 5 more of those little a's. So it will be the 7th root of a to the 5th over, and then my denominator will be the 7th root of a to the 7th, which will give me an a. And then I stop and think, do I need absolute value bars? Think about that for a second. Nope, don't need them. And that's because this was an odd root. So it's only the even roots that we have to think that way. Well, that's a fun process, and we're not even done with all our objectives. We have simplified and evaluated radicals and rational exponents. We have reduced, factored, simplified rational expressions. We have rationalized the denominator. We have not dealt with rationalizing exponents. So rationalizing exponents, we have to remember the rules that we have for raising things to powers. We have properties of powers, properties of exponents. We've reviewed exponential expressions with integer exponents, such as x to the 3rd times x to the 4th, and we know we add the exponents. When you raise a power to a power, you multiply the exponents. When you multiply similar bases, you add the exponents. And finally, we know that we cannot leave a negative power in our answers. So the way that we get rid of that is by using reciprocals. Right now, this is an x to the negative 2 over 1. So what I'm going to need to do is put a 1 up here to flip this whole thing over and make it positive. So that will be 1 over x squared. This is actually going to seem pretty easy compared to some of the stuff that we were doing before. So exponents can also be rational numbers. As I talked about earlier, we can use fraction powers up there. The square root of x is the exact same thing as x to the 1/2 power. So then our rules will all make sense. So x to the 1/2 times x to the 1/2 equals x to the 1st suggests that if we take the square root of both sides here, x to the 1/2 equals the square root of x. And the cubed root of x would be x to the 1/3. The 4th root of x would be x to the 1/4. And we use that to deal with fraction powers. So definition of rational exponents is let u be a real number, variable, or algebraic expression, and n an integer greater than 1. Then we can interchangeably use the rational fraction exponent for what we're using radicals. Those are interchangeable. They are equivalent. If m is a positive integer, m over n is in reduced form and all roots are real numbers, then we will always find that our denominator comes from the root. Notice that's the root of the tree. So if it's on the bottom of the fraction, it's the one that goes down into the ground, and it is the root. So we have a couple of different ways that we can deal with that. We can say, you know what? I'm going to raise this to the 1 over n power, and maybe that's some kind of really nice radical that I can use so that I won't even have to use a calculator, and then raise it to the m power. And that's because with fractions, 1 over n times m is like saying 1 over n times m over 1, and top times top, bottom times bottom gets us right back to m over n. And then in the second one, you'll see they decided to switch that around. They said, you know what, we're going to raise this u to the m power first, then we'll take that radical. We'll use the index and we'll take the root that we need. So either way, it depends on what the numbers are, what we want to use. So numerator is the top of the rational exponent, the power to which the base is raised. So if you're, again, thinking which number does what, just remember the bottom number goes down. It is the root. The top number is like your son, the power to which the base is raised. Your denominator is the bottom of the rational exponent, and that is the root to be taken. So in the fraction, the denominator is the root. It is the index. And once we get used to that, things go very quickly. So on the next page, we see here that we are talking more about what happens when we have these fraction powers and how we can write them. So u to the m over n power, we can split that as putting the n as the index because this is the bottom one, and that's the one that gives you the root, and then raise it to the son, the mth power. But the fraction m over n must be in reduced form. Now, that brings us another problem area. You know, like we talked about earlier, if you have an even root, you have to go back and look at the problem and see when they wrote this problem, could there have been negative answers? What would happen? Well, it's a similar thing here. Here's why. For example, u to the 2/3 does equal the cubed root of u squared. And that's defined for all real numbers u, because every real number has a cube root. Every real number. Uh-oh. Here we see the problem. There are times when we try to take the even root of a negative number, and we know we can't do that. So somebody that looks at u to the 4/6 is going to think, oh, you know what I'll do? I'll just go ahead and I'll make that 2/3. You can't do that because this problem came as an even root. This is the 6th root of u raised to the 4th power. And 6th roots can only be done, so are defined only, when you're putting a positive u value into that. So you'll only be able to use non-negative real numbers for those 6th roots. So this is one of those things we have to watch for. When and if we ever have to reduce a fraction power, we can't lose sight of the fact that we might have to tell people, hey, your domain has changed here. The numbers that you can use has changed. Because as we saw in this problem, it can give us the wrong domain. So we just have to be careful. It's one of those crazy things that shows up when you're going through problems. All right, example 4 says, let's convert these radicals to exponentials and vice versa. Well, here we have the square root, so a little 2, of x plus y to the 3rd. So I know I'm going to have an x plus y here in parentheses. And I think, okay, when I make this fraction, which one of these goes on the bottom? This one. The index goes on the bottom. So that is the quantity x plus y to the 3/2 power. For B, I'm looking at this one thinking, okay, this came with radicals. That means they want it as a fraction power. So I'd better go ahead and figure out what power to raise this x to in order to make all of this work. And I remember this index is always on the bottom, that root of the tree. So that'll be x to the 2/5. And I realize, hey, I'm not done with this one because we're going to multiply similar bases. That means we have to add the exponents. So that means I have to come up with a fraction exponent for this x out here. Well, that's x to the 1st. And since we're talking about 2/5 that we have to add to it, we have to use the common denominator of 5 and make that 5/5. So this will be a 3, and then we need 5/5 plus 2/5, and that will give us 7/5. So we have converted that from a radical into a fraction exponent. Then we look at C. And this one has a fraction exponent, so that must mean they want this put back in radical form. So I remember this bottom number is my index, so this is going to be the cubed root of x squared, and that's times the cubed root of y. And I realize, wait a minute, I can put those together. Those are both cube roots. And as long as they have the same index, we can go ahead and do that multiplication and put them back together. So there it is. D. This is a fraction, a rational exponent. They want this as a radical. So I start thinking, well, how am I going to do that? Well, first thing I'm going to do is I'm going to get rid of that negative by moving this whole thing, z to the 3/2, down to the bottom. Remember, those negatives are for reciprocals. And then I'm going to change that into a radical by remembering the bottom number, the 2, is going to be my index because that's the root of the tree. So it's 1 over the square root of z to the third. And we all know normally we wouldn't leave it that way, but they just wanted us to convert this from fraction powers to radicals. And like I said, it's driving me nuts not to rationalize that denominator there, but that's as far as they wanted us to take this. So an expression involving powers is simplified if each factor appears only once and all exponents are positive. Simplified if each factor appears only once and all exponents are positive. So let's keep going. What that's reminding us is that you can't leave negative powers. We're not supposed to leave those. We've got to get rid of them. So we look at example 5, and we have a here, and sit and think about, what's the easiest way to do this? Leave those fraction powers. Use that. Don't change these into radicals. It's much more difficult to work with radicals. So what I'm going to do here is I'm going to distribute this 1/3 to both of these. So that will give me x to the 2/3, because 2 is like 2 over 1. And when we multiply that by 1/3, it's top times top, bottom times bottom. 9 times 1/3 is going to give me 3. And now this is a problem that we already did in the prerequisites. We said, hey, if you've got similar bases, what you need to do is you need to add the exponents. So I do have a fraction for one of these, and that's an x that has a 2/3. So I think over here about how can I write that 1 for x to the first as something in thirds. Well, that's just going to be 3/3. So we have 2/3 plus 3/3, which is 5/3, and we have 3 plus 2, which is 5. So we have x to the 5/3, y to the 5th. And you think, well, should I do anything more with that? I mean, should I put that in radical form? What do I do? If the problem originally comes with fraction powers, you leave your answer with fraction powers. You don't go any further than that. Let's take a look at B. 3x to the 2/3 and over y to the 1/2, and then 2x to the negative 1/2 over y to the 2/5. Now, we went through some problems that were, well, like this, but they didn't have fractions for powers. They had integers. And my best advice to you was keep it organized. So myself, I would just do top times top. 3 times 2, that's just numbers. That's going to give me a 6. And then I need, with similar bases, to add the exponents. But 2/3 and a negative 1/2 have different denominators. So I start thinking, okay, LCD. 2/3, negative 1/2. It's going to be a 6. So I'm going to have to take 2/3 and multiply it by a 2 on the top and the bottom. And that will give me 4/6. And for the negative 1/2, I'll need to multiply that by 3 on the top and the bottom, and that will give me a negative 3/6. So now when I add those two together to get my power, I have 4/6 plus negative 3/6, and that's going to be 1/6. On the bottom, I have to go through that same thinking. I've got 1/2 and 2/5. I'm going to need to use tenths. So this would be y to the 5/10, multiplying the numerator and the denominator by 5. And then we'd have a y, and we'd multiply by 2 on the top and the bottom for this one to the 4/10, and adding that together gives us y to the 9/10. So it's not the prettiest thing we've ever looked at here, but it's 6x to the 1/6 over y to the 9/10. I'm going to clean that up a little bit so you can see it a little bit easier. And the problem came with fraction powers all over the place, so it is perfectly fine for us to leave our answer with fraction powers. Again, you look at the problem to see how did this problem start, and think, how can I give them the simplified, the best answer in the end that is just like that. Then example 6 is reminding us of some things that you did in Algebra 2, and this would be to simplify in order to combine radicals, because example 6 suggests how to simplify a sum or difference of radicals. We can only, in any algebra, add and subtract like terms. So sometimes we have to do some simplifying first before we can get to those like terms. So I'm looking at A and I'm thinking, well, for 80, 16 goes into 85 times. And then our square root of 125, well, I could use 25 5 times. Well, square root of 16, that's a 4. And the square root of 25, that's a 5. And 2 times 4 is 8. Well, now I can go ahead and do the subtraction because I have like radicals. I have 8 square roots of 5, and I'm going to subtract 5 square roots of 5. That will leave me with 3 square roots of 5. That's the only way that we can add and subtract if we have like radicals. So it is possible that you might not be able to do one if you can't figure a way out to simplify that and make them like radicals. For B, I noticed right away that the square root of 4, hey, that's 2. So I'm just going to write down a 2. And the square root of x squared, well, that's an x. And the square root of y, well, nothing I can do about that. I'm just going to have to leave that there. So I've got 2x square roots of y, and I'm going to subtract. And then I realize if this is a 2, I'm going to have the square root of y squared and a square root of y that I have to deal with back here. So this is 2x square roots of y, but this is y square roots of y. Now, those are like terms. So how do I show somebody, hey, I know these are like terms? Well, we could always do this. Factor it out. And that way people will see, oh, we got this little 2x minus y piece out here, square roots of y. But this has variables in it, and it is an even root. So I need to go back and ask myself, when the person wrote this problem out, was it possible that x and y could come out to be negative? So let's go back and see. X can't. They were going to square that. Following the order of operations, they absolutely were going to square that x first and make it positive. So I have to let people know, if you're going to use my simplified formula, you're going to have to take the absolute value of x. And then, how about the y? Well, this was y to the first, and they're taking a square root. And this was y to the third, and they're taking the square root. The only way they're going to be able to do that is if y is positive. So both of these variables, in order for that original formula to work, both x and y had to be positive. Now, I'm not going to put absolute value bars under here, and hopefully you see why. They're not necessary. And that's because if you go back to the original problem, you'll see that same setup was happening right here. I'll pull a smiley face. This one right here, they were taking the square root of y, and they said, I'll just leave that. So if we put our absolute value bars on our x and our y out front, then that will take care of the author's intent when they wrote that problem. Let's take a peek at C. Square root of 36, wait a minute, that's 6. Square root of 24, perfect squares. I guess 4 goes in there 6 times. So 6 plus 2 square roots of 6, wait a minute, those aren't like terms. Nope, they're not. So all we could do with this one was simplify it. And there's no variables, so I'm not worrying about absolute value bars at all. Let's look at D. Cube roots. Go to my power chart and try to find a cube root small enough to go into 24. Cube root of 8, cube root of 3. Cube root of 81. Now that one's a little tougher. You know, when you're looking at the cube root, you probably will have to go to your chart for a little bit and think, okay, now which one of these will go into 81? But that's 27. And it goes in 3 times. So the cube root of 8 is 2. Cube roots of 3. The cube root of 27 is 3 cube roots of 3. And looky there, we've got like terms. If we have 2 cube roots of 3 plus 3 cube roots of 3, we're going to have 5 cube roots of 3. And there it is. E, square roots. Oh, I should say again with D, I'm not even thinking about absolute value bars because there were no variables involved. Square root of 50, I've talked about that one earlier. That's 25 and 2. Square root of 32, well, 16 and 2 will do that. So this will be 5 square roots of 2 plus 4 square roots of 2. Hey, That's 9 squared, so 2. Cool. Now, if you're worried, how am I supposed to know which perfect squares will work for what? If they give us these problems, generally what you want to do is take the smaller of the two numbers and simplify it first. Because if the problem is going to work, notice in this case the cubed root of 3 had to be added to the cubed root of 3. So the first thing you'd want to try is dividing 81 by 3 in the hopes that you're going to get a cube root. Otherwise it's not simplifiable. So it's kind of an educated cheat. Once you simplify the easier one, then use that knowledge to figure out what you should use to simplify the second one. Now, I bring that up as we look at F. 96, fifth root, no way, not fair. Well, if we're going to be able to do this problem, that 96 better be divisible by 3. So we take 96, we divide it by 3, and we realize, hey, that's 32. Fifth root of 32 plus the fifth root of, or plus, times the fifth root of 3. Running short of space again. I write too big. Notice I wouldn't have even tried any other numbers. You know, if we're going to be able to do this problem, the fifth root of 3, 3 has to divide into 96 or it's not going to work. So this is 2 fifth roots of 3 plus the fifth root of 3. Well, that's really a little imaginary 1 right there. So if we had 2 fifth roots of 3 plus 1 fifth root of 3, we will have 3 fifth roots of 3. And no worries about absolute value bars because this did not come with any variables. So we have been through those objectives. And now we have simplifying radical expressions. And these are the things that we need to do as we work through all of these problems. Number one, we need to remove factors from the radicand. So take out perfect squares, perfect cubes, perfect fourths, perfect fifths. Number two, eliminate radicals from denominators and denominators from radicands. So we know we can't leave radicals in the denominator. That's what we have to get rid of here. And then step 3, combine sums and differences of radicals if possible. If they are like terms, then we can do what we did in example 6. And notice that all of these have where you can look for examples of this. So removing factors from the radicand, that was example 2, and eliminating radicals from the denominators and denominators from radicands, that's example 3, and then example 6 for the last one. So this is a lesson that was supposed to take a day and some change, so that's why this is kind of long. But here is your assignment. You're going to go to Pre-Calc Appendix A1. Feels kind of weird this earlier in the year to be working on page 782, but that's where you need to go. And you need to do numbers 1 through 81 odds. And one thing to think about while you're writing this down is if you have even roots of something, a radicand that has variables in it, do you need those absolute value bars? That's what you need to think about, because aside from that, I think everything that we've seen in this section really has been review from last year. There you go.